Hi there, and welcome from Ventura, California to today's webinar, sponsored by Inside GNSS, Inside Unmanned Systems, and Spirent, and hosted by WebAttract, the leader in thought leadership webinars. I'm Lori Dearman, webinar producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these leading experts specializing in research and development regarding CRPSs and simulation. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Expert panel session with all three of our panel members. Now, we've invited you, along with over 500 professionals across 49 countries, representing a variety of industries. Over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. At this point, I would like to get started by bringing on Richard Fisher, publisher Inside GNSS and Inside Unmanned Systems. We'll take a moment to welcome you and introduce our sponsor as well as our main moderator for today. So over to you, Richard.
Hey, thanks, Lori. Appreciate that. On behalf of Inside GNSS and Inside Unmanned Systems and our sponsor, Spirent, I extend a warm and appreciative welcome to our audience from around the world for today's web seminar. We really value your participation and wish you all safety and wellness for you and your families. Now, I'd like to introduce Adam Price, Director of Product Management and Business Development, the Position and Timing Unit for Spirent, to make a few opening remarks. Adam, over to you.
Many thanks, Richard. Thanks for joining the webinar. This subject matter today is relates to something that we as Spirent have worked closely with industry on over many years, and we've helped customers through some of the challenges that they've seen with the vulnerabilities of GNSS. You've got some very good speakers on today who will be covering everything from the early principles of GNSS vulnerabilities, as we look at things like interference and jamming, moving on through some good content we have. We see Oscar Pozzobon coming on to talk about spoofing and what we need to consider about test plans to mitigate those. And then Sherman really comes back and talks further around CRPA technology and some of the details around, or some of the principles around that. So I hope you find the content interesting, insightful, and also lead you on to think about how you can build robustness into the GNSS systems that you might be developing or integrating into your applications. So please enjoy. Richard, back over to you. Thank you.
Thank you, Adam. Now, I'd like to introduce our moderator for today's webinar. Alan Cameron is the editor-in-chief of Inside GNSS Magazine and the PNT editor for Inside Unmanned Systems. Alan, the floor is yours.
Thank you, Richard, and welcome everyone around the world. I see we have quite a large audience today, and from reviewing the questions that you put on your registration form, a very well-qualified audience and a highly motivated and interested audience. Well, we have the goods for you. We're going to hear today very shortly from Kimon Voutsis at Spirent, from Oscar Pozzobon, Qascom, and from Sherman at Stanford University. I will give you more details on each as we begin each of their individual presentations. But first, let's find out a little bit more about the audience. Lori?
Absolutely. And coming up on your screen should be that very first poll. We'd like to hear from each of you. What one type of RF interference have you encountered most frequently in the past year? And choices there on the screen: unintentional jamming, intentional jamming, spoofing, self-interference, or perhaps none in the past year. So it looks like we have 31% saying unintentional jamming, 29% intentional, 10% spoofing, 9% self-interference, and 21% with none in the past year. Alan, any thoughts here?
Well, Lori, I had the benefit of seeing the results in real time as they were coming in, and it was like a thoroughbred horse race. Unintentional jamming and intentional jamming, exchanging the lead back and forth many times. Unintentional came out by a nose, but the bottom line is that it doesn't matter in a sense. It does in some senses, but the effects of unintentional and intentional jamming are the same on the user. And they are quite prevalent. Together they account for 6/10, nearly 2/3 of the RF interference that people have encountered. And I want to emphasize, we phrase the question, what one type have you experienced most frequently? That doesn't mean that everybody out there is getting all of these. But the one type most frequently. Spoofing is on the rise, as we know. Self-interference is always a concern. None in the past year. These are the lucky few, but consider yourselves lucky so far. Lori, let's move on and begin the webinar. Our first speaker is Dr. Kimon Voutsis, Product Manager at Spirent Communications. He's responsible for providing high-end GNSS test solutions to military, government, and GNSS and space organizations. He's interested in all aspects of GNSS vulnerabilities and threats, for example, spoofing and jamming. He's an author and co-author of several technical reports and publications. He's an associate fellow of the Royal Institute of Navigation and holds a master's degree and a doctorate in positioning, navigation, and timing applications, both from University College London. Kimon, please proceed.
Thank you. Thank you, Alan, for the kind introduction, and thanks to all of those who attend this webinar today. I will be speaking about GNSS vulnerabilities and how to test efficiently your receiver against them, and especially focusing on interference. As we quickly saw from the poll, there is increasing interest from customers. So without any further delay, let me give you an overview of my presentation today. Quick overview about GNSS vulnerabilities, why simulation testing is the most efficient approach to test against them, brief examples about user applications that fall within this category, and the main focus of my presentation will be on explaining what are the key parameters that comprise an efficient testing campaign against interference, focusing on CRPA antennas. And I will conclude with a summary at the end. So different authors use different classification schemes for GNSS vulnerabilities and threats, but I think this diagram encompasses the dimension space of threats and vulnerabilities on GNSS. I'm not going to provide too many details on each one of them, but we can briefly say that these vulnerabilities, spoofing, interference, intentional or unintentional, these act independently and jointly as well. Multipath, for example, occurs naturally, and it's always present whether we like it or not. Also, recently we have seen some increase on cyber attacks, which can be on the RF and non-RF domain as well. So we can have atmospheric threats as well. So why simulation testing is the most efficient approach? The main reason is that it is repeatable, controllable, but most importantly, we can determine the error budget. So if we test on a live sky environment, there is an inherent uncertainty about how much each of these threats that I just mentioned contribute to the error budget. However, if we have a simulator, we know exactly how much the multipath contributes to the errors that we observe on the receiver, how much the interference. So we can characterize the receiver very efficiently. Now, there are lots of user applications. GNSS spans a whole spectrum of different applications, from military to civil applications. So the testing can be very versatile as to what we want to test. In this presentation, I'm going to focus on interference and jamming, but by all means, you will have this slide. If you want to ask any questions about the other user applications, please feel free to contact us. On the lower right part of the screen, I have included a quick diagram about NASA's aviation, voluntary aviation reporting service. These are reports from pilots, reports that they suspect that interference affected the navigation systems of the aircraft, and we can see a clear trend of this event. So there is increasing demand both in the number and the sophistication of these threats. So how can we test efficiently? How can we test efficiently against interference? There are basically two ways. One is over the air, preferably in an anechoic chamber, but if we have permission, we can do it in the field as well. And the other one is in the lab in a conductive manner. There are some example applications, like the focus of this webinar is about SERPA antennas, and there are two great technical presentations that follow from Oscar and Sherman, speaking about in more technical detail about the SERPA antennas. This used to be a clear military application, but recently we have seen that it has come relevant to the civil domain as well. So we have customers who are interested in using SERPA antennas for critical network infrastructure like power grids in order to mitigate some of these intentional or unintentional threats. Also, the testing may be relevant to presume compliance to a standard like aviation standards or the radio equipment directive. So there are many reasons why we need to test against interference and exercise our SERPA antenna. On the right part of the screen, I have an example of a grid of antennas that are installed in an anechoic chamber, just to give an example of how we are emulating the live sky environment. So key parameters on testing. The first one that comes into mind is the accurate power calibration and the modeling. So we need to be able to model efficiently the propagation of the RF signal in the simulated environment. It is important to have a high incident power, up to 0 dBms, for example, and have spectral purity on the output signal. This encompasses both low noise floor and high jamming to signal ratio, for example, up to 130 dBs with respect to the nominal GNSS level. These two concepts are related, but they are not identical. So it is important to be able to have very good specs for both of these two parameters. Another important aspect is how efficiently, how representative is the radiation field we simulate, the number of transmitters we can simulate in our scenario, and what constellations and frequencies we can support in order to provide a realistic wavefront. Especially when it comes to an anechoic chamber, we need to ensure that everything is aligned and synchronized in order to provide this realistic wavefront. So other key parameters when we test against RFI simulation is the carrier phase calibration. This has to be to the degree level, and the reason is when we are exercising our SERPA antenna algorithms for null and beam forming, we need to make sure that the testing instrument, the testing signal we're using is has very good specs in order to test efficiently those algorithms. Another element is that the carrier phase calibration the calibration of the equipment can adhere to a specific ISO standard. For example, this is an important consideration when we formulate the requirements of our testing equipment. How many RF outputs do we need? How many elements do we have in our CRPA? And whether these requirements are going to change in future. We need to have some kind of scalability. Another important parameter is the user friendliness, how well we can generate the amplitude and phase patterns of the transmitters and the reception antennas across different frequencies, because we have different transfer functions for different frequency bands, and also to have a wide selection of realistic waveforms that can occur in the field, like carrier waves, binary phase shift keying, amplitude frequency modulation, pulse modulation, or Gaussian noise. And of course, as an extra option, the customer may be able to introduce their own bespoke IQ streams to replay in the simulation scenario. So scalability is very important. User requirements tend to change over time, and the equipment is not something static. We should be able to support future open signals, like Oscar is going to speak about authentication that is coming for Galileo and GPS, support secure military or encrypted signals, which are not within the scope of this webinar, but however the equipment should be able to support the current and future developments in this area. A very important parameter is the hardware update rate. I'm sorry for the lots of acronyms. I'll explain them as I go along. Hardware update rate and simulation update rate. It's good to have as fast updates on the RF signal that we generate as possible, especially when we are feeding remote motion and we have high dynamics. Another important parameter is how user-friendly is the software that we are using in order to create the scenario and how many parameters we can simulate. Obviously, there is sometimes a steep learning curve to know how to simulate and how to configure all these parameters, but this is where the strength and fidelity of the simulation comes from. Another consideration is the automation. Can we automate the testing campaign, or do we have to manually repeat that? If this is a persistent operation, then it is worth investing on automating these persistent processes. Hardware in the loop, having low latency in the configuration is also very important when we use a receiver to feed back the motion to the simulation, because otherwise we are introducing artifacts that wouldn't be occurring in the real world. And finally, the ability to integrate non-GNSS sensors is key, especially to some military customers, but civil customers as well, because the GNSS is just one source of navigation. We have other sensors that are integrated in a navigation system, so we need to be able to scale up the system and exercise these sensors to the test as well. So just to summarize, this diagram gives an overview of the GNSS vulnerability categories. We have done lots of work with many different customers in each one of them over the last 30 or so years. So we need many webinars to speak for each one of them, but it is important to remember that when we need to test for interference, it is key to consider and the power and carrier phase calibration of the system, how many frequencies and constellations it supports currently and in the future, whether it is future-proof, the signal fidelity and the spectrum purity. We don't want any artifacts like harmonics or frequency leakage when we test the equipment. Otherwise, we are causing the receiver to observe artifacts, masking its true performance. The low noise floor and high jamming to signal ratio for the same reason. And as I just said, we need to have a look ahead on trying to predict what the requirements are going to be in the next 2 or 3 years, and buy a system that it is scalable and can conform with these future requirements as well as the current ones. The update rate is important in order to represent realistically the RF output in a continuous way. Automation options, hardware in the loop options, and sensor fusion also come into play for many customers in an increasing way. So I would be happy to answer your questions later on to this webinar, and thank you for listening. Back to you, Alan.
Thank you, Kimon. And thank you for that presentation. There are a lot of parameters to consider in setting up proper testing. And I know that Spirent works closely with all its customers in designing these. We're going to move on now to GNSS vulnerability testing. We're going to hear from Oscar Pozzobon, who is Technical Director at Qascom. Oscar is the founder as well as Technical Director of Qascom. He's been working in the domain of GNSS security, authentication, and robust navigation for more than 20 years. As Technical Director, he coordinates the 4 units of Qascom of engineering and cybersecurity, simulation systems, advanced navigation, and attack detection systems. He coordinates a number of space programs and activities with the European Space Agency, the European GNSS Agency, and the European Commission, as well as the National Aeronautics and Space Administration and the Italian Space Agency. Since 2008, he has contributed to the design and testing of 2 of the 5 Galileo services. His main interests are space, GNSS, and cryptography, where he has issued more than 50 publications. He's adjunct professor at the University of Padua for satellite navigation. He has a master's in telecommunication engineering and a PhD in aerospace and satellite applications. Oscar, speaking to us from northern Italy, please proceed.
Thank you very much, Alan, and a very special thanks to Inside GNSS and Spirent for the invitation. It's a pleasure to be here today with you. I have 2 parts of my presentations. In the first part, I will give you some updates on the new emerging threats. I believe everyone knows about jamming, spoofing, so I will go a little bit on what's the future, what we should expect. And in the second part, I will provide some details on my vision about methodologies and best practice for vulnerability testing. So, GNSS threats, the past, the present, and the future. GNSS threats are evolving. The real challenge is to predict the tomorrow likelihood of occurrence of the attacks. It's really today's product design. Product design have a long life cycle sometimes, so we really need to know and understand what are the threats of tomorrow. So if you look at the timeline, all started in the 80s, 90s, we had the issue of vulnerabilities. No satellites were there, so not even major security issues. Really, it all started in 2000. Selective availability was turned off. The first jamming events were reported and started to become a threat. We go back to 2010, where we really started to discuss spoofing. In 2001, the Volpe report was released, so we had a decade of discussions about spoofing. And today, we do consider in GNSS vulnerability testing mainly jamming, spoofing, and some cyber attacks that we'll discuss later. What we should expect for the future, the next 10 years, indeed, evolution of threats, and authentication will be an upcoming opportunity, and that will be, I think, that will be the biggest challenges and opportunities for the next 10 years. What for 2040, we really don't know, but consider that we started with the early days, simulators were big and heavy equipment, signal generators, generic, were big and heavy equipment. And today, you see the little picture there on the right, a small tiny chip can do 16 RF channels and generate any signals. So really, the future of cyber attacks and cyber threats will be driven also by the availability of technology. So where are the attacks? Threat classifications, categorization should be and will be the need for the future. We can't really have, without any specific orders, threats in a random fashion. We need to understand the threat categories, and particularly they should be considered in all layers. In all layers, if you look at the diagram there, it kind of takes the idea of the Aussie layers. And when we look at signal layer, it's indeed jamming, spoofing, microning can affect the RF signal level, but we can perform jamming and spoofing at a code level. We can jam with codes. We can spoof only the codes of the signal. When we go to the data level, we can also do data-only spoofing. That, for example, affects SBUS, GBUS. We can also do smart jamming, jamming only specific data. We will see a slide on that later. And then we go up as the evolution of GNSS continues. There will be services that rely on protocol, and authentication is one of them, but high accuracy, whatever, will be the services of the future. If there will be protocol, there will be security exploits on the protocols to consider as well. This is a very practical example of a synchronized spoofing attack. The objective of a synchronized spoofing attack is to perform a position deviation without producing position fixed logs. Anyone can spoof a signal, just switch on a simulator, give some power, you will jam the receiver and then spoof it. The objective here is really to achieve modifications in a way that no algorithms can detect it. And so that requires synchronization with the live signals and also the knowledge of the target position and the dynamics. We've done a lot of cooperations with Spirent as well on this business. And the idea is to have a simulator that can be synchronized with a receiver, and then we can generate synchronized like signals and spoof the receivers in a very precise and stealth approach. Another emerging threat is replay attacks. In a replay attack, they also called security code estimation replay attacks. The idea is to first estimate the signal with a receiver-like technology, and then regenerate them, potentially also changing the ranges with the predicted information. So you see the diagram there shows the high-level architecture of a machine for a reply attack. You need an antenna, you need to detect, estimate the signals, and then you can regenerate the signals with the delays that you want. And the diagram there shows that depending on the antenna gain that you have, that's really the critical point, but you can you can detect signals between 60%, 80%, up to 80% of correct estimation, and you can generate them. And this affects any radio frequency signal. So it's really serious threats that we should consider for the future. The need for sophisticated equipment. This is a very important point. When you use a signal generator, you don't use any Doppler, any specific real effects. You just add white noise for your simulation. The theory is always bright and perfect. All your anti-jam, anti-spoof detection is perfect. They work. And you normally achieve on the algorithm side, on the receiver side, high probability of detection, low probability of false alarm. Things change when you go to a realistic RF environment. So that's why you want to use sophisticated equipment before you go live and test urban, suburban, indoor scenarios where, high multipath, high noise, they highly impact vulnerability testing. Things change. We start to see low probability of detections, high probability of false alarm. They are indeed required for CRPA testing, and they are fundamental for fine risk assessment evaluation. Another new threats that I would like to present, someone might be already aware of this, but it's selective jamming. Selective jamming refers to jamming only some specific data or symbols for some specific objectives. For example, you want to perform denial of service only of a specific service, jamming CRC or jamming some specific navigation data. Or you want to spoof some services and deny others. So the way it works, the way selective jamming works is based on the assumption that most of the bits considered satellite signals reach the receiver with something between 68 and 80 milliseconds difference. So the idea is to jam only some part of the signals. The diagram there shows a spectrogram and the spectral shaping of a selective jamming. You don't see the pulsed part where we do jam only some symbols, but it's something new that we are looking, and it's an emerging threat, particularly considering that future GNSS will include different services at data level as well. The next diagram shows a little bit more the details of what happens in the selective jamming, where you can see that we can introduce high error rate in the data, and only in the data that we want. And it does affect, you see the green line, that's the page error rate. It does affect pages, and you really need to go, in that case, it's 40 dB jammer plus 40 dB jammer that affects signals up to 30 dB hertz. Things change a little bit with the symbols, the yellow line, where again they keep up a little bit more. But still, the main idea here is this new attack allows you to jam, and of course it does work for signals that you know where the data is, so unencrypted signals where you know the position. Something new to consider indeed for the future. So back to you, Alan, for the end of this first part.
Thank you, Oscar. We're going to turn to a few questions from the audience, and then we'll resume with Oscar's presentation. I have one question for you, Kimon. We saw the audience's experience with the number and type of RFI interferences, but what is Spirent's data showing on the current trend as to the number and type of occurring GNSS threats?
Yes, so the current, we know that GNSS threats have increased recently, both in number and sophistication. So until recently, for example, it was very difficult to launch a spoofing attack unless you were a military or government agency, but now you can find open code on the internet and buy cheap RF components and do spoofing. It is difficult to put a number and geography, but we had many recurring demonstrations recently, for example, in Syria or the Black Sea, and certainly with personal privacy devices, there is an increase of jamming threats. Now, some of these threats are fully some of these events are fully reported, but there is certainly an under-reporting trend. So yes, just to summarize, numerous reported events and increasing number, both in sophistication as well. But I can, if someone is interested, I can provide more details offline. So yes, thank you, Alan.
All right, more details available on that offline. Kimon, another question for you. When you talk about the scalability of a test system, how far can we go, and is there a trade-off between scalability and performance?
Yes, this is an interesting question, and we have customers asking about how scalable and how flexible are our systems. We have lots of customers who initially bought a system and then upgraded. For example, they added features like multipath modeling or constellations, frequencies, or embedded interference, or bespoke features, you name it. And they can do that in the field. They don't have to return the equipment back to us. So sending back the system to the factory is rather the exception than the rule. So I would say that our systems are pretty scalable and future-proof. Now, about the trade-off between scalability and performance, I can give you an example. For example, a single simulator box can simulate up to 320 channels, and for satellite signals and multipath as well. And if this is not enough, we can add many boxes together. We can synchronize them without compromising on performance. So I would say no. There shouldn't be a trade-off between scalability and performance. Yeah, thank you, Alan.
No trade-off between scalability and performance. All right, we have some questions coming in regarding the first part of Oscar's presentation, but I'm going to put them on hold and return to them in our question period toward the end, and ask Oscar, before we ask Oscar to resume, we will have another poll question, please, Lori.
Sure. Coming up on the screen is that second poll question. And we'd like to hear from each of you. What is your level of experience with simulation testing for signal vulnerability? And options there are: we currently incorporate simulation testing for signal vulnerability in our processes. We have not done so and have no plans to do so. We have not yet done so, but wish to take this step, or we have not yet accomplished this, but have taken concrete steps in this direction. So have the results there on the screen. Any thoughts there from you, Alan?
Well, the majority have, I should say the plurality, if I have my terms right, have incorporated simulation testing. This is a good sign. Although, as Oscar pointed out, the threats are evolving. They don't stay still. So simulation testing must continually be updated to reflect the evolution of RFI threats and other vulnerabilities. Little less than 1/5, perhaps 1/6, have not yet done so and have not yet made plans. I won't lecture you, but consider yourself, consider this a schooling, this webinar. We have almost 1/3 of our audience have not yet undertaken testing but wish to do so. Clear interest. Spirent, take note, and not yet accomplished, but are taking steps in this direction. We can sort of lump those in with the first group, people who are actively engaged or progressing towards testing. Let's resume with Oscar's presentation, GNSS Vulnerability Testing Part 2. Oscar.
Thank you, Alan. So why testing in simulation? We can prevent threats before occurrence. It does support risk assessment, analyze the impact on the receiver. We can check the impact on specific environments. It can be played in a repeatable ways. So you can also think about doing massive vulnerability testing. You have your batch of simulators with a batch of receiver. You have thousands of attacks. You go through all of them 24/7. And then when we look at the threats to consider, I like to give you this hint. Please consider a new vision, not just jamming and spoofing as it used to be, but consider the objective of the attack. If we split by denial of service and deception, you will see that both spoofing and jamming can do both, can perform both of these attacks. So you can achieve denial of service with jamming, smart jamming, which is a more sophisticated way of achieving. It's not just pushing high kilowatt power, but code level jamming, for example, bit level jamming, as the selective one, for example. Data spoofing is a type of denial of service. Sometimes you transmit the family's data in the future and you deny the receiver because it gets the existing family's data and it doesn't work anymore. So, and cyber attacks. Cyber attacks, it's a new thing. They're coming out. We see them more and more. We do test a lot these type of attacks. There are some specific scenarios. You send data, you create a divide by zero situation, and the receiver crashes. So look careful for cyber attacks because it will be indeed something to consider for the future. And then when we then look at deception, confusion, changing the PVT, this indeed can be done with spoofing, mikoning, which is a replay of the signal, or detection and estimation and replay attacks. So look at the objectives, because really security testing should first start from your requirement, from your objectives, and not just for what the simulator capability is. Looking at the different approaches of vulnerability testing, you can test by known attacks. So you just get your equipment and you pick up all the known attacks, as I mentioned before, and you do massively test all of them. That's one approach. You can also test by the known vulnerabilities of your equipment. So you have a track record, you know the vulnerabilities of your equipment, of your receiver, or the applications, and you go test through of them, you fix, go back for testing. So that's another approach. You can test by security objectives, like you want to navigate over an entire area for 4 hours and you want to make sure that your application is not jammed or spoofed. So these become high-level objectives. And we normally do tests by comparing the nominal KPIs with the security KPIs. So if you do test your equipment, your receiver, or your applications by looking at the KPI availability, integrity, precision, accuracy, and so on. The security KPI normally look at what is the probability of false alarm, probability of misdetection, time to alert, and any other security KPI that you might have. Again, on the vulnerability test planning, it's very important to define the simulation realism. What do you want? What do you need? Do you want to simulate the attacker location with the attacker dynamics, the channel conditions that the attacker is going through, if there will be multipath during the transmission of the jammer or spoofer, the antenna gain, the antenna pattern of the attacker with respect to your receiver? You know, just imagination, you can go as further as you can, but it's really important, because the more you achieve realism, that the more your success on testing the protection will be close to reality. Define sensor fusion simulation. This is very important. In the diagram on the right, you see that position solution today is achieved with so many options, not just the GNSS, from inertial sensors, data that can be corrections or integrity, the antenna, whether that's a standard antenna, CRPA, you will see later, or any other PNT sources. Those need to be simulated when you perform the attacks, because they strongly affect the sensor fusion algorithms. And I give an example there on the left bottom. That's an example of the application risk assessment, let's say in the aviation domain, where GNSS is most likely fused with the INS or IRS. You will deal with the inertial system accuracy with respect to the GNSS accuracy. So assuming that just GNSS can be spoofed wouldn't lead to anywhere, because normally the flight computer will check the different navigation sources. And so it is very important to consider, for example, in this case, the different accuracy, the degree of freedom that the cyber attack could have. You could move, for example, in the tunnel within the inertial system accuracy, you could move the position of GNSS without triggering any alerts or any exclusions on the sensor fusion part of a flight management system, for example. So again, it's very important to consider the whole system, the whole navigation system, not just the GNSS receiver. Finally, the future authentication services. So we've been talking about spoofing and at system level. Most of the systems today have been working on potential solutions, which is authentication. Indeed, military level, there are other solutions for protecting from that, but in the civilian domain, all codes and data are publicly available in the ICD, so anyone can take them and regenerate them. And authentication shall mitigate these threats by protecting and authenticating the source of the signal. Galileo will launch soon the Open Service Navigation Method Authentication, OSNMA. The system is currently ready for that. We're just waiting for the final go for the SIS testing campaigns, and GPS as well as considered Chimera, chip message robust authentication. The other systems that we see a lot of proposal going on for other systems as well. The main difference between Chimera and OSNMA, that OSNMA at the moment protects the data only. So the benefit in Galileo was to achieve a very fast introduction of the service, as it's only data modification. So potentially billions of receivers in the world could perform simply firmware update and receive OSNMA. Where GPS is a chip-based solution, so that we require update of the satellite. It's in fact coming in the new satellites, and we require new hardware as well. Authentication will be an opportunity to test receiver-based anti-spoofing with system-based services. So look closely at the updates for both GPS and Galileo and other systems. It's an interesting opportunity. Conclusions. Security is a continuous process. New protections means new threats. I always say that security is the only area where the more we invest and the worse things get. So the need for vulnerability testing is a fundamental part of the security process. Security requirements shall define the level of sophistication and realism required, including application level realism, and authentication services will be the next decade opportunity to test protection mechanisms. Thank you very much, and back to you, Alan.
Thank you, Oscar. And thanks for that glimpse at the coming authentication services. That's going to be a very interesting technical aspect to begin exploring. We've had some publication on it in the magazine already, but there's much more to come. We're going to go now to the CRPA portion of our program to be presented by Sherman Lowe, a senior research engineer in aeronautics and astronautics at Stanford University. Sherman's work focuses on navigation safety, security, and robustness. At Stanford, he was an associate investigator for the Federal Aviation Administration evaluation of enhanced LORAN and alternative position navigation and timing systems for aviation. He currently leads work examining GNSS interference and spoofing detection and mitigation. He has more than 100 conference, 20 journal, and 14 magazine publications to his credit, and holds 8 issued U.S. patents. He has a PhD from Stanford and bachelor's degrees from the University of Maryland. He teaches an undergraduate navigation class at Stanford, and now he's about to teach us. Sherman, take it away.
Thank you, Alan, for that nice introduction. I also like to thank our sponsors, Inside GNSS and Spirent, for the invitation for me to present here, as well as my colleagues for their inputs into this presentation, and all of you guys for being here during this troubling time and to try to improve on our GNSS capabilities. So my talk is on control reception pattern antennas, SHRPAs, for civil applications. The talk is divided into 3 parts. First, we'll just go over the relevance and suitability of SHRPAs in civil applications. Second part, we'll go over the basics of SHRPA technology. It's fundamentally how SHRPAs work, what are the fundamental kind of algorithms they employ. And the last part, we'll talk about research and development of SHRPAs in the civil community. SHRPA and its underlying technologies have been around for decades, and the military has been using it for lots of applications. In the GNSS side, in the 1980s and 1990s, phased arrays and the GAS-1 GNSS SHRPA receivers were developed and being deployed. So it's been around. SHRPA's utility in GNSS applications, as we've heard before, is in reducing the incoming jamming energy relative to the desired signal. And you can see why that's a very valuable thing in the military, and that's why a lot of investment has been made in SHRPA for that domain. However, until recently, a little or no investment has really been made on the civilian side. I think many years ago, we used to think, well, what's really the utility of this when we have rare interference events that would merit the use of this. And so it was thought that the benefits wasn't really adequate to merit both the cost and complexity of a SHRPA, and also the challenges, the institutional challenges of getting a SHRPA. There's restrictions on the technology. But today, we see more and more instances of threats to GNSS. Oscar mentioned quite a bit of those. The relevant question is, can we create, not whether we should have them, we should, but can we create a SHRPA that's appropriate for civil use? That means technology having the capabilities that we need, while also meeting the restrictions on export controls that a SHRPA has to meet. And so, I think you all know this, but GNSS is safety critical infrastructure from power grids to aviation to intelligent transportation to financials. And as GNSS has proliferated, so has the number of threats. GNSS jamming, especially the deliberate kind, is increasingly common, and we're starting to see spoofing capabilities become really accessible. You could do it for a few $100, maybe even less. And so, so this makes SHRPAs very important, because SHRPA is going to address both of these vulnerabilities. And not only is it important, it's perhaps potentially necessary and even life-saving. And so I'll give an example of one application that we think of in the civil community for SHRPA. It can provide this. It can provide an essential robust element in critical infrastructures that utilize standard GNSS. And the application is precise time synchronization, as provided by GNSS, is important in services from telecommunication to power to financials. But if we use just a standard GNSS receiver antenna, that's vulnerable to a lot of threats. And so we can use SHRPAs to provide an accurate, cost-effective, and robust way to synchronize ground stations. And these ground stations could be individual places that need time, but also can be distribution nodes for timing. So they can be powerful, for example, terrestrial transmitters, such as an ELRAN or a cell tower or a DME that can act as a distribution node to provide timing to more places. And so concepts for doing these robust terrestrial timing transmissions have been investigated by several U.S. governmental efforts, and they're still ongoing. I know there are a couple of tests that are planned this year for that, but they're all going to rely on some way of providing a precise time source, and I think SHRPA is one of the ways that we can do that. The other issue I mentioned is export controls and restrictions on SHRPA technology. Many countries have restrictions on its use, sale, and export. Prior to 2015, all SHRPA technologies were subject to restrictions in the U.S. But fortunately, at the end of 2014, a new rule was enacted that essentially permitted some possibilities for development of an effective civil SHRPA. Specifically, what it basically said was they changed the restrictions to the technology to be limited to Sherpas with 4 or more elements and certain capabilities in terms of depth of null they can form and how quickly they can adapt. So if what was outside this restriction, you could create a Sherpa that was non-ITAR regulated. So next I'm going to cover kind of fundamental concepts in how Sherpas are implemented. There are many flavors of Sherpas, but they all have some basic fundamental things that they do. Once again, traditional or standard antennas are known as fixed reception pattern antennas, or FERPAs. While we think of a Sherpa as an array antenna, that's not really the strict definition. More fundamentally, a Sherpa is an antenna that can adaptively change its gain pattern, the gain pattern of its reception. So anything that can adaptively change its gain pattern versus a traditional fixed gain pattern. The gain pattern is controlled by generally electronically adjusting the relative weights and phases between the antenna elements. Now, I use elements in a generic sense because it doesn't have to be separate antennas. It could be separate things coming out of the same antenna, as we'll see later. And so how does that work? Sherpa works effectively by weighing the signals from each antenna separately and combining the results. For those of you who are equation-oriented, it's a pretty simple equation that you see below. The weight is a complex weight, meaning we're adjusting not just the amplitude, more importantly, we're adjusting the phase. By adjusting the weights, this changes how Sherpa effectively listens and allows formations of nulls and beams. And so, for example, let's think about just a basic two-element Sherpa, two antenna Sherpa. The relative phase between the incoming signals at each of those elements will differ when they're coming from different directions. So if we just change the relative phase between using those weights, we can cause constructive or destructive additions of the signal when we combine the signal from those two elements. And so that's classically what we're doing with a Sherpa. We're nulling or beamforming, whether we have constructive or destructive interference. The fundamental function of a Sherpa, though, is to, at least for our purposes, is to form a null. And GNSS Sherpas, some of them, that's all they do. They just form nulls. Nulling essentially minimizing power. And without beamforming, all our degrees of freedom can be essentially dedicated to creating nulls as long and reducing noise. So we often call this unconstrained because it's not constrained by some restriction on where we can form the nulls. Forming beams creates a constraint on nulls that we can form, but beams help us concentrate the GNSS signal energy, and so that's great because it ensures that we don't get rid of desirable signal energy. There are a couple classes of way we form these beams. There are two major classes. One is the class that tries to maximize signal to interference and noise ratio, SINR. The other one is in the class MS&E class, minimizing the mean squared error. We'll talk about them next. So we'll do this by example. A prototypical SINR class algorithm is minimum variance distortionless response, or MVDR. In MVDR, a constraint is created such that we have a beam that is formed at a specific look direction, and that's the direction where the signal is coming from. Then the nulls are then formed to minimize energy outside that constraint, outside that beam that's looking at a specific direction. This is expressed through our weighting matrix. Our weighting matrix provides constraint. So shown here in the plot on the right is WM+1. I'll explain why we have a subscript like that. We change that weight over time to adapt, basically. And how quickly we change this weight is basically our ability to adapt. This technique is good for static applications. So MVR is good for static applications where you know your orientation towards the desired satellite because you're looking at a look direction. So you need to know where the satellite is relative to you. So that's where it's good. But if you didn't know your orientation, it's really hard to do this technique. So the second class, and that's the MS&E class, the MSE class, the least mean square error class, and a representative algorithm in that class is least mean squared, LMS. And in this class, the constraint that's used is a replica of the signal. And the algorithm builds this constraint such that it looks at the resulting mean squared error between what we receive versus our reference, what we're referencing. And so that's our signal. And so we try to minimize the error between that. And so you don't need to know the direction. You just need to know the signal you're looking for, and you're trying to minimize the difference. Makes a lot of sense, doesn't it? This technique is useful for dynamic applications because we don't need to know the look directions. We don't need to know our orientation. But because you're you're looking at a reference signal, it's susceptible to other replicas of that signal, such as multipath or worse, spoofing. So effectively foreign beams in direction of the target signal, even that happens to be multipath or spoofing. Both algorithms are relatively straightforward to implement in an iterative method, and this is really important because these iterative methods are good because they don't require long integration times to get the estimation of the covariance matrix and its inversion, which is needed to form the weighting matrix in both these cases. And what I'm showing on the right is the iterative implementation of each of these methods. Now let's talk about nulling. Nulls are used to minimize undesired energy. Nulling is generally done by power minimization, as most of the power in the band should be noise. This makes sense as, GPS is below the noise floor, so when you're reducing noise, you're effectively reducing all that interference and crud that you don't want to have, so it's effectively anti-jam. With beamform, if we add beamforming onto nulling, the minimization only occurs again on energy outside the constraint. Each null or beam requires a degree of freedom, so the number of nulls formed depends on basically the number of elements in the antenna. So it depends on the spatial degree of freedom. I should be more specific, and we'll see why that's important later. So in summary, the implementation differences between beam steering and nulling. We'll talk about the implementation nulling only adaptive antennas. First, with beamforming, we get additional energy from each antenna or antenna element. And so if we have 7 elements, we could theoretically have 7 times the energy. Oftentimes not fully the case, but that's the theoretical limit. But this reduces a degree of freedom that we have for nulling. So the benefit from beamforming versus nulling kind of depends on the number of elements you have. The more elements you have, the more gain you get from the beam, but you lose an element for nulling. Also, as each satellite's in a different direction, you have to generate a different beam and different composite signal for each satellite. This results in a separate calculation and a separate composite signal for each satellite. And so if we have 12 satellites, we have to come up with 12 different signals. So it's more computationally intensive and you need to process a different signal output for each satellite. So you need a more bespoke receiver to do this. Now, if we do nulling only, we don't get that concentration of signal, but it's useful because we only have one composite signal. So we're just taking everything we get, we're minimizing noise, and we're producing one composite signal. And that composite signal can go into any receiver that we have because they all take one signal. And so it's very nice to retrofit into any existing receiver. And so while it potentially is less effective, especially as GNSS approaches the noise floor, it can be applied more broadly to existing receivers. One more item I'll talk about is so beam steering, null forming are spatial processes. We are limited by the number of elements in the antenna in terms of then spatial degrees of freedom and how many directions we can handle. Another technique that's often employed is time or frequency domain processing to form spectral nulls. And time taps or frequency bins, if you do it in the frequency domain, from measurements are combined to form frequency nulls. You can see that spectral null on the plot on the right. And so oftentimes this is done with the spatial processing in a SERPA. And so often you'll hear about SERPAs doing STAP, spatial time adaptive processing, or SFAP, spatial frequency adaptive processing. Just note that this is not exclusive to SERPA, but it's often done with SERPAs and can be employed on FERPA. And by combining all these techniques, we can get very powerful SERPA, the STAP or SFAP SERPA that often you might hear about. So we'll go on to the last part when we're talking about, examining research and development efforts on civil SERPA. I think there's really a lot of exciting work going on here in this area by a number of groups doing in that domain that are, that can be applied to the civil sector. And so we'll just cover a few that I'm familiar with. So, of course, I'm familiar with our work in SHERPA. And so our work in SHERPA started in 2010, really with the goal of developing a SHERPA suitable for civil and aviation applications. This means using low-cost, commercial, off-the-shelf COTS parts, preferably because you want to make sure that you can mass produce it. You want to make sure it's not exorbitantly priced for these markets. And so we developed a real-time flexible software implementation capable of supporting multiple frequencies. Again, aviation, we want to use both L1 and L5, and a variety of antenna configurations. And most importantly, being able to use low-cost antennas. We started out with expensive survey-grade antennas, and we worked down to very low-cost antennas that we bought off of Amazon. Turned out that we were able to use software to help compensate for the deficiencies of some of the hardware, not all the deficiencies, but some of the hardware deficiencies. These low-cost antennas there's a lot more variation in them. And so that's good because what it means is you can trade some hardware costs for, which are recurring for non-recurring engineering costs for the software development to compensate for it. More recently, we've been working, we and some other organizations really have been working on a concept called a dual polarization antenna, which is able to capture and utilize both left-hand and right-hand circularly polarized signals. The interesting thing about a DPA, a dual polarization antenna, is it can be built with a patch with 2 feeds. And here you see it. You see an example of our dual polarization antenna. DPAs then actually may be considered a SHERPA because we can use those 2 signal combinations to create a null in one direction. So really, it does have an adaptive gain pattern, despite the fact that it is a single antenna. And often is a single antenna COTS patch antenna. In fact, ours is something we bought, an antenna that we bought on the internet. It wasn't a bespoke antenna. It was just some antenna that somebody sold as a traditional GPS patch. And so we developed it for both anti-jam and spoof detection purposes. But what's interesting enough is that some other groups have looked at this and combined the 2 ideas, combined the idea of an array antenna with a dual polarization antenna. And so researchers at DLR have built and tested an array antenna with DPA elements. And this antenna was demonstrated to have better accuracy under nominal conditions because what it does is combines energy from the right hand and the left hand circular elements in addition to all the multiple antenna elements. And so it's able to do that during nominal conditions. And during interference conditions, it performed better than that same array antenna when it was only using the traditional right-hand circularly polarized components. And the references to those to that work is below. For our SHERPA and DPA work, it was critically important to test the system to further develop our processing algorithm. So we participate in several field exercises to evaluate performance. These exercises are very informative, but they're also challenging logistically. They're often in extreme environments, in extreme conditions. This is the far north of Sweden. You see in the snow. We had to deal with reindeer and the Lapland reindeers that were there. They're often in the middle of the night, as we're done in the U.S. That's the only time we're allowed to interfere with GNSS and not cause too much of a problem. And they require a lot of paperwork, coordination, approvals, and funds to participate. And so these are important, but they're few and far between, and they're really challenging. And so it was really important that we develop at least a basic simulator capability to do some fundamental tests in between these field exercises. And so to really have a good rapid development of SHERPA technology, I really believe it's important to have both good simulation capabilities as well as occasional field tests to kind of validate and maybe see stuff that you see how it really works in the field to kind of validate what you're doing, to kind of balance out all that work and to inform what you need to improve on next. And I just want to end up with one example of our results from the test. This is from many, many years back. We were able to go take our SHERPA, and that's the SHERPA that we saw on the slide before. It's just 4 simple antennas that we bought from Amazon, to lay them on the roof in any configuration and had our software figure out its layout. And we tested it against all sorts of different jammers. In this case, it's a simple broadband jammer, but we tested against SWEP CW and other jammers. And fortunately, in this test, we were able to control the jammer, so we were able to have it do a step up jamming profile. So we slowly increase the jamming by a few dB every 30 seconds or so. And we're able to test it against how different receivers perform with it. A FERPA, when it started losing lock, versus our SERPA, versus our using two different techniques, both MVDR and power minimization. And we were able to quantify basically the gain that we were able to get from the SERPA versus these other techniques. So in summary, SERPA for the civil market is achievable. People have products out there, and we believe it's practical and has a lot of uses. There are many forms and implementations of basic SERPA technology: beam steering, null steering, time and frequency processing. And finally, research and commercial development of SERPA is ongoing, and I think it's exciting, but really requires many means of testing to really kind of further and improve those capabilities. So with that, back to you, Alan.
Thank you, Sherman. We're going to take a quick look at resources available for your further information. There's a lot more information available to you, 2 ebooks and a data sheet. Lori, let's have our third poll, please.
Absolutely. On the screen there is poll number 3, and our question to you: what is the most common threat affecting GNSS signals? In this case, your response options are short-range jamming, chirpers, personal privacy devices, etc., area-wide or region-wide deliberate GNSS attack, Black Sea, Syria, etc., spoofing for criminal or other law-evading purposes, scheduled signal operator outages, or perhaps something else. So there we have it. Alan, any thoughts here?
Well, clearly short-range jamming is the most prevalent, but to me it's remarkable that area-wide or region-wide deliberate attacks constitute nearly a third, according to our audience. And this is, it's hard to say what threat is most serious, because any threat can be serious to any particular application, but something that affects a whole area or region is very serious indeed. Spoofing seems to be less of a concern for our audience, although we know that it is on the rise, and the other 2 categories a bit, don't want to say insignificant, but certainly bringing up the rear. We're going to go to questions to our panelists now. Sherman, the first question for you. You alluded to the challenges, some of the challenges for field testing SERPAs. You want to expand on that a little bit, and how to balance field testing versus simulation testing?
Yeah, so we're talking about challenges of field testing SERPA and how to balance that out between field test versus simulation tests. Field testing, I think, is very vital. I think you learn things in field tests that you may not learn anywhere else, and we certainly have done that. But that being said, it is hard. At least in the U.S., there's not very many places where we can't run our own interference source. We can't run our own spoofing source. There are only certain entities, even within the government, that can run that, and they have to get permission to run that. So these are very involved events. They often have to be conducted in very remote places, and they have to be conducted in the middle of the night so they don't affect anything. So already the environment is pretty hard, and you're subjecting your equipment to some pretty extreme conditions as well. And so there's that. Additionally, you only get one shot, and so if it doesn't work, then your next shot is in a year. So you can't. It's hard to iterate that way, and so that makes that challenging. And then finally, because we're not necessarily running the test, we can't fine tune the test and run it to exactly the way we want to. We work with the people who are running the test to kind of try to draw up a test plan that makes sense. But you often realize in testing that that's best done iteratively. try something. Oh, okay, yeah, maybe we should tune it this way, and do this instead. And you don't really get that. You can't. It's really hard to do that given the test environment. And so therefore, I think that's where the complement in simulation really helps. That we can really start kind of working out these cases, working out what we really want to see, what we really want to test. I'm glad Kimon mentioned stuff about having antenna setups within the simulation models. That's critically important. Our ability to form nulls and depths of nulls are dependent on how precise our antenna is, how well calibrated they are, how well we know their gain/phase patterns, things like that. And so I think simulation tests are absolutely necessary to complement and kind of inform what we want to try to do in the field tests.
Thank you, Sherman. Kimon, anything to add to that about including antenna configurations in your simulations, or anything else that Sherman just said?
Yes, I briefly touched upon that. So it is very important to be able to provide the user-friendly way to model the antenna patterns, the phase and the gain for different frequencies as well. Because it is critical to model the phase array correctly and have the resolution that you need in order to exercise properly the null and beam forming algorithm. So yes, we've got industry contacts. We've got long-term relations with customers who do this application. So we've got a good fund of knowledge and experience in this area. Yes.
Terrific.
Thank you, Alan.
Thank you, Kimon. Oscar, next question is for you. You mentioned a number of attacks, some known and some are new. How does the user know, or how do we know which ones we should consider in our application?
Well, okay, so I think the best approach is to perform risk assessment. So you start from the likelihood of occurrence of a specific attack. So you mentioned that there are some new, some old, and when you look at the likelihood of occurrence, you really should consider, is the equipment to perform the attack available, what kind of expertise, also the regional possibility to occur, to happen. You multiply that for the likelihood of success, which is, let's assume that someone will perform that specific attack. What is the probability that will really penetrate my receiver and achieve success in performing that specific attack? And you finally multiply that for the impact that will have on your application and your receiver. You end up with a conclusion, classical risk assessment, high, very high, low, very low, whatever it is. You will then set your risk appetite, whatever is the threshold for whatever is suitable for you, and we decide whatever is above these thresholds, I want to protect it, and that's where you will understand, we will know which are the attacks that you want to protect for your application. That's my view.
Thank you, Oscar. Kimon, in terms of simulator architecture, somebody wants to know which is better, FPGA or GPU?
Right, FPGA or GPU. So the question is coming often, and it is really about whether it is worth to use a bespoke GNSS simulator architecture that we are using with FPGA instead of a more generic GPU approach. I must say any hardware architecture and configuration has pros and cons, but the question is, for what application are we intending to use this hardware architecture? So Spirent simulators employ a software-defined radio SDR architecture, which is specifically designed for GNSS signals and under all dynamic conditions. The reason we don't employ generic or open architectures for data processing or signal generation is because this cannot be optimized to the level of required performance for GNSS testing. because we need to maintain the radio frequency fidelity, the timing, the latency, especially under high dynamic conditions. Also, we develop this architecture from end to end. So we have better control, we can support it, we can maintain it, and thus we eliminate the risk of relying on third-party tools and hardware. It is easy to use an IQ stream with downloaded observation data, but we have worked a lot over the last 30 years to fine-tune the highly complex models to represent accurately the constellation and the operational environment of the receiver. So otherwise, the receiver just mimics the poor performance of the testing equipment instead of showing its true performance characteristics. So the choice between FPGA and GPU is really dependent on the application space, the user requirements, and the future requirements. But I think I would be happy to provide more details offline if needed. Yeah. Thank you, Alan.
All right, thank you, Kimon. A couple of questions now about cost or relative cost. We won't get into any exact figures, but one for Sherman and one for Kimon. Sherman, somebody wants to know, what about low-cost SERPAs? What are the challenges there? What are the trade-offs in using a low-cost SERPA?
So in terms of low-cost SERPAs, there are a couple things, right? You need the receiver processing to be able to do that, and unfortunately, most of the receivers that we kind of invest a lot of money on and build in mass quantities are smartphone receivers, which are not designed to do kind of that SERPA processing, and so that's one cost issue, and that I think that has to I don't know how that has to get addressed by the marketplace. The other cost issue is antennas. It used to be, I think, when we started our work, we used to think that, we'd have to have a really nicely calibrated and very refined array of antennas. So these antennas have to be not have a lot of variation. And I think with our work, we were able to show that we could compensate for some of that with software. And I think that would, at least if nothing else, help lower the cost on that end, lower the cost of the antenna array. We still, it's not going to perform as good as a nice, an array of really high quality, low variation antennas, but you could still get a lot of gain from kind of lower cost, more variable antennas. And I think that's important. The antennas that we started out with were survey grade antennas, which were, in the $1,000 per antenna range. So we went to very low cost antennas. I bet we can, use these mass market antennas to build an array. So at least that end of the hardware is not. I think we can make low cost at the other end in terms of receiver side. That's the challenging part.
Thanks, Sherman. Kimon, a similar question for you. In your realm regarding simulators, someone wants to know, why do I need to buy an expensive simulator for testing instead of using a less expensive one, or perhaps just Live Sky for free?
Yes, of course, it depends on your application requirements and your budget, but it is important to be aware that whether you're a manufacturer or you're a tester or integrator or a testing consultant who conducts black box testing, or whether you're conducting white box testing as a manufacturer, it is important to ensure that the input signal in your test is correct and reliable. Otherwise, you will not be able to distinguish between the errors of the testing equipment and the device under test. This applies both to simulation testing or live sky testing as well, because there is this inherent uncertainty in terms of what the RF environment is. So I think this is really where the strength of using a reliable and fit-for-purpose simulation comes into play, because if you can ensure that the input signal is correct and reliable, then you can focus on the receiver characteristics. And I think this can justify the value of perhaps more expensive equipment. So you get back your money in a different way. Yeah, thank you, Alan.
Thanks, Kimon. A bit of a common thread running through yours and Sherman's replies is you've got to look at the application. You've got to look at your own requirements. And if I may prejudge Oscar's question, I think answer to this next question, I think it's going to enter into there. Oscar, you described several different methodologies and approaches to vulnerability testing. How do I know which one I should follow?
Thank you, Alan. Well, that's a good point. I think you should start with two major stream. The one where you are required to do testing in a specific way, whether it's government control or safety applications, for example. So in that case, you have specific requirements and standards to follow. Aviation DO 229, where it defines the jamming tolerance level. Or in the automotive domain, for example, here in Europe, we have the Senelec EN 16803, ETSI 103246, NIST and ISO also, they have standards for vulnerability assessments. So that's one way where you have standards you have to follow. If you don't have standards, you rely back on what I mentioned before. So you just perform your own risk assessment and you do whatever is better and best for your business and for your application. That's my view.
Thank you, Oscar. We are about to wrap up our webinar. I want to address very briefly one question that came in about SERPAs and that is, what are the current regulations authorizing the use of SERPAs for civil applications? Obviously, this is a key concern. I had a bit of back-channel talk with Sherman about this. It's a very complex question, and people are still trying to sort it out. I would say the best answer I can give is pay attention to upcoming issues of Inside GNSS. We are going to try to address this question as full on as we can. Obviously, there are things that, since SERPA is a classified technology, part of it is now declassified. And as Sherman said, it's still a little bit in the sorting out stage. So we'll try and bring as much clarity to the issue as we can in an upcoming issue of the magazine. Well, I want to thank everyone. I want to thank our sponsor, Spirent. I want to thank our panelists, Kimon, Oscar, and Sherman. I want to thank our excellent team of organizers, Lori and Terry, and I want to thank you, the audience, for attending. This has been, from my point of view at least, a very profitable and educational webinar. I've picked up a lot, even though I've reviewed the material 3 or 4 times as we prepared this. Always going through one more time brings more out of the woodwork, so to speak. I'm going to ask each of our panelists for a concluding comment, and then we will bid you all a fond and adieu. Kimon, closing words?
Yes, thank you very much, Alan. It has been great speaking to this panel for GNSS vulnerabilities. It is a hot topic, and I'm sure there is going to be lots of interesting news to come in this area. So watch this space.
Watch this space indeed. Oscar?
Well, thanks again. Thank you very much for the workshop. I think it was excellent. And well, what I can say, security is never ending, is a life cycle. Don't expect we will ever reach 100% security. New protections, new solutions will mean new vulnerabilities. So just stick with a plan, with a life cycle, and keep your eyes open for the upcoming GNSS authentication services, particularly on Galileo. We all look forward to new testing and new opportunities. Thank you again. Thanks, Alan.
And Oscar, I want to extend a special thanks to you for all the work you've put in during the last 3 weeks as we've prepared this webinar. I know circumstances in northern Italy, well, they're difficult everywhere, but they have been particularly challenging where you are. So thank you for what extraordinary effort in an extraordinary time. Sherman, last words from you.
Thank you, Alan, and thank you all for being here today. I appreciate your attendance. So last words, I think, adaptive technology will grow in the civil community. I think there's no doubt about that. We should also remember that this is not the only way that people are working on to address the interference and spoofing threat. And as Oscar said, look out for all these other things coming on the horizon, such as authentication and everything else. Again, if you have any more questions, please feel free to contact me and let me know. I'll try to address them as best I can. Thank you all.
Thanks, Sherman. We want to extend a special thanks again to Spirent for making this webinar possible. Adam?
Many thanks. Thanks for everybody for joining. Much appreciated, and I hope it was a fruitful webinar for all, and look forward to these kinds of events in the future. So thank you very much, Alan.
Thank you, Adam. Well, we've done it again. We've employed an hour and a half of our time, of your precious time, very fruitfully in bringing ourselves up to date. Of course, the up-to-date level keeps moving out in front of us, and we have to keep chasing it. As I said, and as our panelists have said, keep your eyes on this space, meaning the vulnerability space. Keep your eyes on the webinar space for continued updates, and keep your eyes on the magazine, and the website will bring you the latest information just as quickly as we can. That's enough for me. Thank you, everyone, once again, and over to you, Lori.
Well, thank you, Alan. And of course, thank you all for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.